Problem number 11, we're being asked to simplify. For part A, this is a complex fraction. I have one fraction divided by another fraction. I can just rewrite this as a multiplication problem. Dividing by 6 over x squared is the same as multiplying by the reciprocal, x squared over 6. And then I've got some common factors to divide out. Here a 2. And then for the x's, this single x would get rid of one of those x's up top. Multiply across, and we're all done. 1 times x is x, and 1 times 3 would be 3. And we're all set. Letter B is also a complex fraction, but it's a little more complicated looking. I think what I would do is use this technique. Find the LCD of all the little fractions. There's only one little fraction, 2 over x. The LCD would obviously just be x. Take that number and multiply it by the large numerator and the large denominator. When you do that, you won't have any more little fractions. On the top, I have some distributing to do. X times 1 would just be x. 2 over x times x, the x's would cancel, leaving me with just 2. And then x times x on the bottom would be x squared. Can I take this any further? Well, unfortunately, x minus 2 doesn't factor, and I don't have any x minus 2's on the bottom, so this is as simple as it gets. Letter C, it looks like I need to subtract these two fractions. Y plus 1 doesn't factor, and y minus 1 doesn't factor, which means they're their own factors. I'm going to have to fix this one by multiplying by y minus 1, and fix the other one by multiplying by y plus 1. I've got to get a common denominator. Remember, parentheses on the top are not helping me, so let me get rid of those. If I distribute this x to the top here, that will become xy minus x for the first fraction. And I have y minus 1, y plus 1 here. And then the second one, let's see, I'll have xy plus x when I distribute. And again, y minus 1, y plus 1. I'm now ready to subtract. Be careful here, because when you subtract, all the pieces of the second numerator need to be subtracted. I should probably go ahead and write that out. So I'll have xy minus x, then I'm going to have to subtract each of these pieces. So I'll have minus xy, and then minus x there. When I distribute that subtraction to both pieces, the bottom stays the same. And then what? I do have xy minus xy wiping out on the top, and then I have negative x take away x, which is negative 2x. The bottom continues to stay the same. Everything is factored, I just don't have any common factors, and so I'm finished. Here would be the final answer. Problem number 12. Sine x is going to be replaced with the letter w. So I'm going to have to take each expression here, make sure that I can see all the sine x's, and then everywhere I have one, I'll replace it with the w. Letter A is obviously very easy. This is just going to be 5w. Letter B. Now let's see. What does sine squared x mean? It means the whole sine x is being squared. Well, sine x is w, so this is going to become w squared. Letter C, I don't have a sine x, I need to make one. Well, I can make one by reciprocating the cosecant x to the bottom. The 20 will stay there on the top, but cosecant x reciprocates and becomes sine x, and now that I have a sine x, I can replace it with my w. Final answer here would be 20 over w. In letter D, I have a cosine squared x. I don't want that. I want a sine x. What I can do in this instance is take advantage of the Pythagorean identity. So I know that sine squared plus cosine squared equals 1. If I solve that for cosine squared, I get cosine squared equals 1 minus sine squared. We use this version of the Pythagorean identity a lot. So I'm going to rewrite that expression, and I'm going to replace the cosine squared with 1 minus sine squared. It's the same thing. Let's clean this up a little bit. I've got 4. I'm going to distribute minus 4 and then plus 4 sine squared x. Well, the 4's drop out. The only thing I have left here is 4 sine squared x. What does sine squared x mean again? It means sine x all being squared. And you can see the final answer. It's just going to be 4w squared. And then part E is easy. We've already got everything in terms of sine x. We've determined already that sine squared x is just w squared. So this is going to be 5w squared. And then plus 23w and minus 4. And we're done. Problem number 13. We're given 6 different functions here. 3 of them are identical. We want to use the calculator to determine which. All we need to do is graph them, and the ones that match are obviously identical. So let's start with y equals secant x minus cosine x. On the calculator, I'm in radian mode. I'll go to the y equals area. For secant, I'll have to type that 1 over cosine x. So secant x minus cosine x. I think I'll just use the trig zoom window there, zoom 7. And so there's my graph. I'm going to start adding in some of these other ones. So now I've got cotangent x sine x. Back to the y equals. Let's see, for cotangent x, I'll have to enter that one as 1 over tangent x. So there's cotangent x and then times sine x. And I'll hit graph. And obviously that's completely different, so that's not a match. Next I have sine squared x secant x. How will I type that in? For sine squared x, I'm going to have to take sine x, put it in a parentheses, and then square it. So that would be sine squared x. I'm multiplying that by secant x, which is 1 over cosine. And I'll hit graph. Aha, now that one looks like it overlapped with the blue graph from the start. So at least now we know what we're matching. So the first one and the third one are identical, not this one. I just need to find one more. I have cosecant x plus sine x next. I'll just replace the red one here. Cosecant x, 1 over sine x, and then plus sine x. Looking to see what happens with the red one. Nope, so that's something different, so that's out. Okay, how about tangent x sine x? Tangent x times sine x. Again, the red one is the one we're focusing in on. And it looks like we found it, so that's another match. I won't worry about the last one. We knew there were only going to be 3. Now, problem 14 says, can we use algebra to figure out why these 3 came out to be the same? Let's see, let me focus on the ones that look simpler to me first. So I'm going to start with this one. Y equals tangent x sine x. Tangent x is the same as sine x over cosine x. If I multiply that by sine x, what I'm going to end up with is sine squared x over cosine x. So that's this one. But take a look at this one here. I have sine squared x secant x. If I simply reciprocate the secant x to the bottom, it turns into sine squared x over cosine x. And so the two pieces match. What about the third one? Well, this one looks a little trickier. Let's try switching to cosine. So secant x is 1 over cosine x. And then I have minus cosine x. I'm going to write it cosine x over 1. Let me try to subtract these. I'm going to need a common denominator. It would obviously be cosine x. So I'll put cosine x and cosine x. That turns this into 1 over cosine x minus cosine squared x over cosine x. Now I can subtract. I get 1 minus cosine squared x all over cosine x. But look, 1 minus cosine squared x, that's one of those versions of the Pythagorean identity. If you move things around, you discover that 1 minus cosine squared x is equal to sine squared x. And so once again, this thing comes out to be sine squared x over cosine x. We've demonstrated why all the graphs matched. It's because you can take all three of these and rewrite them as sine squared x over cosine x.